Hello and welcome to another lesson. Today's lesson we're going to be starting Unit 2, Boolean Algebra. So if you've never dealt with Boolean Algebra before, this might be a little bit of a crazy experience. It's not like regular algebra. It deals with logic and true and false, as opposed to just x's, y's that represent numbers. So we're going to get into that a lot. But the learning objectives here, we're going to define what it is. We're going to define what addition and multiplication mean in terms of Boolean. It's going to be plus and it's going to be multiply, but they're going to mean something a little different. It's going to turn out that addition also means the word or the operation or, and multiplication means and. So that's going to be interesting. State the Boolean algebra properties. All right, we'll get into that. We're going to do some work with networks, which you'll see soon are very visual ways of representing Boolean algebra or Boolean logic. We're going to create and analyze expressions. We're going to read and create simple Boolean circuits, and we're going to simplify expressions and their related networks. So lots of interesting stuff going on in this unit. Not quite related to what we did in the previous unit, but all totally relevant in terms of computers and how computers tend to think, or what we can call thinking. So the topics we're going to cover, you can read this list. You can take a look at this little comic or little meme I've put up here, and maybe by the end of this unit this will make sense to you. 1 plus 1 is 2. In binary, 1 plus 1 is 1, 0, or 2 in binary. You should get that. In Boolean algebra, 1 plus 1 is 1. Visible confusion ensues. So let's move on and see what we got going on here in Boolean algebra. So as an overview, if you're wondering what it is, it was created by this mathematician named George Boole. So he took ideas of logic, oops, didn't mean to cross that out, took ideas of logic and combined them with algebra, and he combined them to produce what he called Boolean algebra, or what was later called Boolean. I mean, no surprise. The guy's name was George Boole. It's a type of algebra in which the values of the variables can only be truth values, which in this case means it can be true, which means 1, or false. So literally the entirety of this type of algebra only deals with ones and zeros. So you can see it probably works quite well for computers, but that's going to come up real soon. That idea of true equals 1, false equals 0. But for now, I'll just say that it's a fact. And then he said it's developed for logical operations. It was developed for logical operations to help us think through things logically, and is the main theory behind when we design digital hardware or circuits, or just the decision-making process in general for computers. And these are what the networks look like. So they might not look like anything right now, but it turns out in the end we're going to see that this is an AND gate. This would be an OR gate. Anything that looks like those two things or those things respectively. And it's a way of, for example, taking information coming in. We have two pieces of information, for example, and then if they're both true, then we get some resulting thing come out of this line. Some, it's almost like you code something and say, if A is true and B is true, if they're both true, then we're going to go ahead and follow this path. And then whatever this is, we don't know what that is, but if they're both true, if one or the other is true, then we're going to spit out this final answer, okay? But that's getting ahead of ourselves to try and make sense of what's going on here. I just wanted to give you a little bit of introduction as to what those networks mean. You don't need to be able to handle them yet. So Boolean algebra, once again, Boolean algebra is a logic-based decision-making system. It helps us make decisions. It helps us understand the whole idea behind if you have this and that, what happens. Like binary, it deals in ones and zeros. But unlike binary, they don't represent numbers. They represent ideas of true and false. They don't actually represent numbers. So that's something you're going to have to get your head around. It's just the ideas of true and false. So 1 is true. Never forget that. 0 is false. Don't forget that. You can almost think of it like on and off, for example. So it says here underneath, from another perspective, 1 means that there is something or a circuit is on. So to have something be called 1 in Boolean means it's either true or there's something or the circuit is on. So we can say that 1 here means that we have a light bulb on, for example, the circuit is on, or we have a closed switch, that would be on, or 1. For 0, 0 means we have nothing, or that the circuit is off. Or in this case, we have a light bulb which is off, or we have an open switch. They all mean the same thing, but just don't worry too much about where I'm going with this yet. Just try and get it in your head that 1 is the idea that you have something, or that you have a circuit that has things flowing through it. You have a light bulb on, for example. Or 0 means you have false. You don't have those things. You don't have a light bulb on. You don't have a closed circuit. And you just don't have anything. So it'll start making sense soon. Finally, there are 3 operations only in Boolean algebra. Only 3 operations. You have addition, multiplication, and complement. We're going to see soon that addition has the plus sign, but it actually means and. I'll write it in capital because it often is written that way. Multiplication is going to be the dot, and it actually is going to mean or. And complement is like saying not. There's really not a good symbol for that. There is. We're going to see that it's A with a bar on top, but really it means not something. So the complement of true would be false because it's not true. Just the opposite. It flips from on to off. So addition in Boolean algebra. In Boolean addition, we call it plus. It's also called or. So we have this plus sign with or. If you were to look at this diagram here, it means this is a Venn diagram. You don't actually need to worry about what this means right now. I'm just putting it here so it all connects later. Eventually, you'll make sense of that. It says we use a plus symbol, plus, to represent Boolean addition. So let's just focus in on these sums. Okay, 0 plus 0, 0. All right, that checks out. 0 plus 1 is 1. That checks out. 1 plus 0 is 1. That's fine. 1 plus 1 is 1. That doesn't quite seem right. So I've put this little box here. What is strange about these results? Well, I'm going to write out what I think is strange about these results, and you see if you agree with me. First of all, 1 plus 1 equals 2 normally. And so we'll say, so why 1 now? Or why 1 in Boolean algebra? And once again, I'm going to write this out. You tell me if you agree. Okay, so what I wrote here was, it helps to think of 1 to mean on, or to have something. So either have something or you don't. And remember, this plus sign means or. So follow me through this logic, okay? It says we either have 0 or 0. All right, do we have a 1? If we have a 1 for either of those, it would be 1. Well, we don't, so we just get 0. In this case, it's saying if we have a 1 for either one of these, 1 or the other, it will give us a 1. And we do have a 1 here, so it gives us 1. In this case, it says we must have 1 for one of these. 1 or the other must be 1, and if so, we'll get a 1. Okay, we'll have it. And in this case, look, we either have 1 for either of these or both. So in this case, all we need is 1 to get 1 back. In this case, we have 2 1s, so we can't have more on. It's just, it is on. So it's actually should make sense in Boolean algebra. You know, you turn a light switch on. Let's just say this, okay? We have a light switch here. We have a light switch here. And we're going to have a light bulb which turns on if either one of these switches is turned on, 1 or the other or both. Okay, I turn this light switch on, it turns that bulb on. I turn this light switch on, it turns that bulb on. I turn them both on. I still have a light bulb being turned on at the end because it met that condition. So it's the same idea, one or the other gives light. Well, 1 plus 1 will still give a light bulb which is on. So that's the idea behind this 1 plus 1 equals 1 in Boolean. Remember, they're not actual numbers, they're the idea of true and false. So really it's like, if this is true or this is true, then the final answer will be true. This is the big idea. Okay, so just bear with me if it's not clicking yet. It'll make sense soon, I'm sure of it. And this logic gate here, that's the name for the symbol that we use. That's called an OR gate. That's the shape that it has, almost kind of like this sideways Star Trek looking insignia. That's OR. We'll get to that later. So we can represent logical results in something called a truth table. And this can look a little bit intimidating at first, but just follow me here. It starts by giving us two possibilities. We have two inputs. So A and B we can think of as inputs, and our output is going to be this, A or B. Remember, let's not forget this. This means OR. It also means plus, but it really means OR. So look at this. It says if one or the other is 1, we're going to end up with 1. Okay? If A or B is 1, the resulting statement is 1. That's our OR rule. So look at this. Is one of these 1? Of course it is. And so in this case, I get the answer 1. If A or B is 1, the answer is 1. So it's 1. If A or B is 1, in this case B is 1, we've got 1. One or the other must be on in order for this to give 1, so it doesn't give 1. Okay? If you think of it as plus, take A plus B, that's fine too. Just take these numbers and add them together. But remember, in Boolean, 1 plus 1 actually equals 1. So be careful. You can think of a plus as an addition. That's fine. You can think of OR as addition. It's not going to hurt anything. But just be careful, because 1 plus 0 is 1. 0 plus 1 is 1, 0 plus 0 is 0, but 1 plus 1 is actually 1 because it means on or true, not the actual number 1. So I find that to make the most sense of this, it really, really helps to see it in action. So this is a website you can go to yourself. If you have the PDF, you should just be able to click on it. I'm going to bring it up on my computer here, and you can see me walk through it. Okay, so here we go. This is the website on the right side. You can find this yourself. It's called Logic Gate Simulator by academo.org. And I've scaled it so that we can put it on the page. But let's just try to help you understand. Sorry if it's a little bit small. So on the left side here, it says recreate the following circuit. So I'm going to do that. Right now I have one on and off switch, and I have this output. I need another input, so I'm going to add an input node. All right, there we go. And look, I need an OR gate. So I've got a list of possible logic gates. I'm going to put an OR, add it. Now I have an OR gate in the middle and an output. So the idea is that on the right side here, this would be A, it would be B on bottom. I'm going to connect them. You can try this yourself. In fact, you should try it yourself. And then look, one or the other is not on. So neither one is on. That's off, that's off. So the whole thing is off. So that's actually one of our first states. 0 and 0 equals 0. This one here is off and off. Off or off is off at the end. We normally put zeros in this course at the bottom, so I'm just going to put it there. Let's try if A was on. Look what happened. A is on, B is off, but the logic gate says that only one or the other needs to be on in order for the final answer to be on. So I'm going to say 1, A is 1, B is 0, because A is on, B is off. It still was on in the end. It still gave me 1. Okay? In other words, this one currently is 1, B is 0, the final answer, output, is on, so it's 1. Again, think of this logically. That's all this is. This logic gate says if one or the other is on, the final output is on. Now, let's try another one. What if only B was on? What do you think? Pause the video, take time to think about it. What am I going to get? There I go. B is on, and the final light. We can call this like the light bulb over here. that's on too. So it's almost like in your house, if one or the other light switch is on, it's on now. Okay. You can also think of it as a parallel circuit. You know, if you had a parallel circuit, if you've ever done some physics, if you have some current coming in this way, you only need it to go through one of these paths in order to light up the light bulb. Okay? You don't need the other path. It could actually not even exist. Or the other path could be used. So it's like a parallel circuit. I can put that down just in case that's helpful to you. It's like a parallel circuit. So let's finish the truth table. If they're both on, of course, one or the other is on because they're both on. So that's why this truth table looks the way that it does. Okay, and if I zoom back in, you can confirm this with your basic math. 1 plus 1 equals 1. Well, in Boolean, that's true. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. So this all checks out. It says experiment with different combinations of input to confirm the truth table. Well, I did that. It's all good. No problem at all. Activity 1 extension. Use the website to help you complete a truth table for A plus B plus C. Or in other words, A or B or C. So I've filled in the table for you. I've put in the different combinations. I do recommend that you try this. I'll show you how I would set it up. You would move your circuits over, put another input in because we need a third input. This OR, I'm just copying this. We need an OR and a second OR gate. Okay, OR. And I'm going to move this over here. Again, I'm just matching what I see. It comes out of this and actually goes into the other OR gate, and then this is the OR gate that happens. And so, for example, 0, 0, 0 is 0, well, off, off, off gives a final answer of off, so that's that. What if A, B, and C were all on? A on, B on, C on, it gives a 1. What if A and B were on, but C was off? It still gives us an output on. So if you do this long enough and you play with these, just flick switches and see what you can make happen, and then fill in the truth table. Turns out that as long as one of them are on, it'll give us our final answer, which makes sense. If we have 1 plus 1 plus 1, it gives us 1 because the maximum number we cap out at is 1. 1 plus 1 also gives us 1. Even 1 equals 1. So as long as we see a 1 in here somewhere, I don't know what I was trying to accomplish there. Basically, all of these are going to give 1. Because that's how Boolean addition works. As long as we have one or the other being 1, we're good as gravy, right? That's the idea. So hopefully you're catching on to this. If not, go back and watch it. And of course, if you ever have any issues on specific concepts, there is extra time in class built in for you to ask those questions. So do not be shy. This is your education, not mine. Make sure that you take advantage of the opportunities I'm giving you. You can get very far by asking good questions to me. So just jot down the page, jot down the topic, and I'll find it for you. All right, multiplication in Boolean algebra. Well, just like addition, we have, oops, this is got a typo here. I was going to say, just like we had addition, we also have multiplication in Boolean algebra. And in this case, it's not or, it's called and. So instead of a plus sign here, we use a dot symbol, just like you've probably seen in regular math class. 5.x.y is not too unusual. And it just says, consider the following products. And in the back of our mind, we're going to think about and now that we know a little more about logic. Okay? 0 times 0 is 0. Okay, that makes sense. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. All these make sense. So I'm just going to say nope. All good. Anything strange about this? No. It checks out in terms of regular math. But also, it should check out in terms of your logic. The only way that you're going to get a 1 out of this is if 1 and 1 gives 1. Okay? Only if you have both on do you get on. So for example, if they're true and true, That's the only way that this circuit will happen. So we can say on or true. I'm just trying to think of ways that it could make sense to you. So for example, it's, you check the weather and it says it's going to be raining today. So you're like, okay, if it's rainy and cold, I'll wear a jacket. All right? If it's rainy and cold, I'll wear a jacket. And B multiply. All right? But if it's rainy but not cold, I'm not wearing a jacket because that doesn't count. Or if it's not rainy but it's just cold, I'm not wearing a jacket because I'm stubborn. Or it's not rainy and it's not cold, well, I'm definitely not wearing a jacket. So that's what it means for and. Both of the situations need to be true in order to spit out this truth value of 1. So just something to think about as we work through this. I'll show it again in the circuit form later. And this is the shape of the and. So it's like a giant, like a big D, pretty much. Just a rounded edge and a flat edge on the other side. Okay. And once again, you can look at the Venn diagram if you're curious. That's what it would mean. If x and y are both true, then we have this intersecting point in the middle that'll execute our operation. So I wanted to mention, if you're finding this a little bit brain-breaking at the moment, that's normal. Take time to let these ideas settle in your brain, because Boolean is a whole new way of thinking. It's a new form of logic that you might not be comfortable with. So let it sit in your brain for a while, and if you don't get it by the end of this video, that's okay. Take time to sit and think about it for a while and go back through it. But in the meantime, let's do the truth table. It says logical results like those in Boolean algebra can be presented in truth tables. This is a truth table, just like in the last situation. It says fill in the truth table for A and B. So let's look at this big box here. You can compare this addition operator to an AND operation. So once again, I made a typo. I think by the time you see this video, this will be fixed. You can compare this multiplication operator to an AND operation. If A and B are 1, the resulting statement is 1. Otherwise, the statement is 0. So that's our rule to go with. And so 1 times 1 is 1. 1 times 0 is 0. Okay, this is the idea here. So actually, I'll keep these symbols in here just so you know that we can use them. I'm going to make it red just to differentiate it from the plus. 0 times 1 is 0, and 0 times 0 is 0. So generally speaking, the truth tables, we don't write any of these extra symbols here in red. None of these. But for you to know what's happening here, this is to help you out, just the extra little bit of notation. And again, why do I know it's A times B? Because this column is asking us to take A and take B and then do our AND operation, or our multiply. Okay? The A being this and the B being that. So hopefully I'm not confusing you too much. Take time to make sense of this. Activity 2, I'm going to set up the same sort of thing as I did before, but I'm going to do an AND. So here I go. I've got my website back up. Again, you can follow the website yourself. And we want to recreate the circuit. I've got 2 inputs here, and I want to put an AND gate, or a logical AND here. I'm going to connect them and see what happens. So think of this as both of these need to be on. One and the other needs to be on in order to get the proper output. So right now, it should be no surprise that no matter what I do right now, if I click on just one, I get nothing. So I can start filling in this table. Oops, sorry. If A and B are both off, then of course I get nothing. A and B must be on to be on, so let's check that. A and B, if they're both on, do I get a light? Yes, I do. If one is off, it turns off. But if they're both on, I get the light up. So if A is 1 and B is 1, then I get my 1. Compare this to the previous truth table, you can see that I'm actually getting the exact same thing as before. But this is more visual. What if I only have A on? If A is on and B is off, well, I get nothing. They both need to be on. What if A is off and B is on? Once again, I get nothing. Because the whole point of the AND gate is to only allow signal through if both conditions are met. The first condition and the second condition both need to be met, and then I get my output. And again, I'm saying conditions because these don't actually need to be light bulbs or switches. They could be anything. This could be the idea where it's like, if it's a rainy day and it's cold outside, then this is when I'm going to wear my jacket. Only when this lights up will I wear my jacket. So if it's not rainy, I'm not wearing my jacket. If it's not cold, I'm not wearing my jacket. If it's not rainy or cold, I'm definitely not wearing my jacket. Okay? Sorry to give such a silly example, but this is all it comes down to. It's a logic gate, a computer generated situation where the computer can actually help us figure out what the answers to our question should be. So computers are very good at logic because they can deal with ones and zeros very well. Activity 2, which is the extension here, is very much like the other extension that I gave you, except it has the 3 inputs and you're using a triple-ended AND gate. So you can probably guess that the only situation here that would allow this output to be on was if all of these were true. And that should make sense because only when 1 times 1 times 1 is true do I get a 1. Think about if I have a 0 in all of these. 1 times 1 times 0. This 0 kind of messes up the whole thing, doesn't it? And there's a 0 here, so that's going to be 0. There's a bunch of zeros on the next line. All of these conditions are going to give me 0. Because, of course, think of this as a multiply. If there's a 0 in there, anything times 0 is 0. So this is like a series circuit. If you have a resistor, you have another resistor or a switch, and you have another resistor, from point A to point B, or let's say whatever the input is, you have a signal kind of going along, and you have an output at the end. The signal is just happily going along, and it goes along our resistor, and yeah, the current, woohoo, woohoo, I'm going to make it. And then someone says, nope, I'm going to cut out this resistor. Well, you're not getting an output out of this. You can have ones all day. You can have a 1 here and 1 here, but as soon as you get a 0, as soon as someone cuts off your series circuit at some point, you're toast, man. You're not getting an output. So this is akin to a series circuit. If you've done physics, it should make some sense. If you haven't done physics, don't worry about it too much. It's something to help you if you've done those things before. Finally, activity 3, which is I'm calling it a challenge. I want you to recreate this, which has an OR and an AND logic gate, and then you can go ahead and try to fill in this part of the table. I definitely recommend that you try this. You can get a lot of intuition out of this. You can make a lot of sense of the situations if you play with an interactive tool. And just do that, play with it. It might not be the most exciting game you've ever played. Maybe you'd rather be playing something else. But it's something that will help you develop the understanding. And there's no replacement for that. No one can take that away from you. Let's do one more operator, which is a really quick and simple one. It's complement. And what it means is if we have something, for example, this circle X, let's just say we have that. Well, the complement is everything else. It's not that. So we call it not. That's why it's called not here. We use a variable with a line over it to represent complement. And 0 is the complement of 1, 1 is the complement of 0. It's just opposites. And for example, the complement of true would turn into false. Again, all opposites here. So 1, its complement is 0. 1 complement is 0. 0's complement is 1. 0's complement is 1. So I just kind of stole this from the previous tables. In fact, we don't actually need all that. We can shrink it. If we had A and complement of A, the only possibilities are either 1 and 0. The complement of 1 would be 0, and the complement of 0 would be 1. So this is a perfectly fine table. You don't need these extra rows. I just put it here to compare it to the previous one. What's the shape for a knot? Well, this is our NOT gate. And again, if you want a way to remember it, it's a triangle, but it has this dot on the end. It's kind of a knot dot. I like to call it the knot dot. I'm sure it has a fancier name. But the circle on the end means complement or not, which means whatever comes into it. For example, if we had a 1 going in, a 0 would pop out. or if we had a 0 going in, a 1 would pop out. Okay, that's all a complement does. It just flips what we gave it. So exercises. It says find the result if a equals 1, b equals 0, and c equals 0. I'm going to do this first exercise for you, and then I'll leave the rest for a future video. Let's look at this first question. Let's rewrite it with our given information. We know that a is 1. We know that b is 0, or false. We know that c is 0, also false. So I have 1 times 0 plus 0 negated plus 0. And remember, plus really means or. Dot really means and. And, well, there's also not. It's hard to write the line on its own. I mean, there's something underneath it, of course, but yeah, complement. So let me show you how to break this down. We're going to look at this piece under the brackets. Think BEDMAS. You do brackets first. You can treat negation or complement or not like a bracket. I'm going to do what's under it first, and I'm going to do the multiply first, because it's basically a multiply. What am I left with? What's 1 times 0? 1 times 0 is 0. I'm going to copy the rest. Now I'm going to stay in those brackets. I'm going to call them brackets. They're not really brackets, but they're the best thing we have. In fact, in some books, in some textbooks, negation looks like this. You put the tilde sign in front. You put this sign in front, and it means not that. So it is kind of like brackets. You can think of it almost like there's these hidden brackets here, okay? In any case, we want 0 plus 0. Well, that's still 0. That's still 0. And the negation on top still exists. And then we still have that plus 0 over on the side. Maybe I'll move it over just so you can see that I'm lining everything up. And then say, what's not 0? It's 1. Not 0 is 1. Right? That's from our negation rule. And so not 0 is 1. We have plus 0, or 0, 1 or 0 will give a 1. 1 plus 0 also gives a 1. So this is how this is done. That's quite a lot to take in one day, and so I'm going to leave it here to give space for you to be able to go through this. And then in the next class, we'll pick up where we left off right here. I hope that made some sense to you. I know it can be a little bit brain-breaking, but take time to let it sink in. Try these examples, and perhaps the examples on the following page, and see if you can get some logic. Good luck, and I'll see you in the next video.